What if the structure meant to protect an entire region for 5 centuries was already doomed before the first drop of rain fell? That question haunted investigators long after the water receded, because the dam that collapsed overnight had been praised as a masterpiece of modern engineering, certified to last 500 years and publicly declared impossible to fail. In the months before its completion, engineers spoke with absolute confidence. The foundation was solid rock. The concrete mix exceeded international standards. The spillways were oversized, the drainage systems redundant, the safety margins generous on paper. Every press release reinforced the same message. This dam was built not just for today, but for generations yet unborn. It would outlive cities, governments, and even the engineers who designed it. And yet, on a quiet night, after just one prolonged rainstorm, the unthinkable happened. The rain itself was not extreme by historical standards. It was heavy, persistent, but well within the parameters the dam had been designed to withstand. No record-breaking rainfall, no once-in-a-millennium storm, nothing that should have triggered panic. Meteorological reports described it as significant but expected. For the engineers monitoring the structure remotely, it was supposed to be another routine stress event, the kind every large dam experiences dozens of times during its lifespan. But beneath the surface, something was already wrong. As night fell, subtle changes began to occur inside the structure. Internal pressures shifted in ways that did not appear on standard dashboards. Seepage sensors registered minor anomalies, numbers still within acceptable limits, small enough to be dismissed as noise. A few readings flickered, then stabilized. Nothing alarming enough to justify shutting down operations or alerting downstream communities. That false calm was dangerous. Large dams do not fail suddenly without warning. They whisper before they scream. They communicate through tiny cracks, microscopic movements, changes in vibration, and water behaving in ways it should not. But those signals are only meaningful if someone is willing to listen, and if the system is designed to interpret them correctly. That night, the water level rose steadily. The reservoir pushed against the dam's face with increasing force, a force the designers were certain they had calculated correctly. After all, the models said the structure could endure far worse conditions for hundreds of years. What no one openly discussed was how much those models depended on assumptions about soil behavior, drainage efficiency, construction consistency, and human decision-making. Somewhere deep within the dam, water found a path it was never supposed to find. At first it moved slowly, exploiting microscopic weaknesses where materials met imperfectly. Concrete is strong under compression, but it is not immune to time, temperature variation, and internal stress. Water, patient and relentless, does not need force when it has access. It only needs time, and that night, time was all it took. By the early hours of the morning, the internal balance of the structure had shifted. What had once been evenly distributed pressure was now concentrating in specific zones, places that had been flagged years earlier during construction reviews as low risk and therefore left unchanged. No alarms screamed, no emergency protocols activated. The dam still stood, silent and imposing, exactly as it had the day before, until it didn't. The first structural failure did not look dramatic. It was not an explosion or a visible collapse. It was a silent internal breach, a moment when water pressure exceeded resistance in a critical section, triggering a chain reaction that engineers had confidently declared impossible. From that instant, the dam was no longer a structure holding back water. It was a structure being taken apart from the inside, and once that threshold was crossed, there was no stopping what followed. As the rain continued to fall, the forces inside the dam multiplied, accelerating a process that had already begun long before the storm arrived. The disaster that unfolded over the next few hours was not caused by rain alone, but by decisions made years earlier, choices hidden behind reassuring language and optimistic projections. And that raises a disturbing question. If a dam designed to last 500 years could collapse in a single night, what else have we been told is safe, simply because the math says so? If you're following this story and feeling the weight of how fragile even the most perfect engineering can be, take a moment to engage. Leave a comment below, sharing your thoughts. Do you believe this disaster was inevitable, or could someone have seen the warning signs in time? Your insight matters, and it helps everyone understand the human and technical factors behind such catastrophes. Also, if you Want to keep exploring the hidden truths behind industrial failures and learn how small mistakes can trigger massive destruction? Make sure to hit the like button and subscribe to the channel. By doing so, you'll stay connected to these compelling stories, helping preserve lessons from events that shaped history in dramatic ways. The dam, when first conceived, was a marvel of modern engineering. On paper, it was flawless. Blueprints stretched across desks in corporate offices and government agencies, diagrams showcasing spillways, drainage systems, and reinforced concrete buttresses that promised unprecedented stability. Every calculation had been double-checked, every safety margin meticulously accounted for. Engineers spoke with confidence that rivaled hubris. This dam would outlast its creators, a structure so robust that it could be handed down to generations without question. Construction crews worked tirelessly, adhering strictly to design specifications. Concrete was poured in uniform layers, reinforcements measured to the millimeter. External consultants validated every phase, issuing reports that emphasized perfection. The materials alone will ensure centuries of reliability, one consultant wrote in an internal memo. The kind of language that inspired trust, but also bred complacency. There was an aura of invincibility surrounding the project. Stakeholders believed in it, workers believed in it, the public believed in it. No one considered the subtle imperfections that only time, water, and stress could reveal. But no matter how precise the design, theoretical calculations can never fully predict reality. Soil compaction varied across the foundation. Minor inconsistencies in the concrete mix created pockets of vulnerability. Tiny gaps in joints, invisible to the naked eye, allowed water to penetrate in ways that engineers had not anticipated. These imperfections were trivial when isolated, almost meaningless on their own. Yet, when combined with natural forces, they became a ticking time bomb. By the time the dam was complete, it had already gathered a quiet history of warning signs. Engineers noticed microcracks forming in sections that experienced the highest pressure. Instrument readings occasionally spiked, suggesting slight shifts in the internal structure. These anomalies were documented, but the language in reports softened the urgency. Within acceptable range, insignificant deviation, not a cause for concern. Management encouraged optimism. Projects with delays or heightened scrutiny were politically inconvenient. When the first heavy rains came, the dam performed as predicted, or so it seemed. Water levels rose gradually. Sensors reported data consistent with the models, and for a moment, confidence held. Behind the monitoring room screens, engineers assumed the structure was behaving perfectly, exactly as it was supposed to. Yet beneath the surface, water was probing, seeping through. Microfractures navigating paths the models had not included. The unseen movements of water began to exert force on weak points that no diagram could fully represent. As the night progressed, subtle shifts accelerated. Sections that had been safe were suddenly under disproportionate stress. Vibrations increased in intensity, a barely perceptible hum that only precise instruments could detect. This was not a catastrophic failure yet, but it was the first whisper of what was to come. The dam, perfect on paper, was revealing the hidden truth that every structure carries secrets that calculations cannot erase. The illusion of safety that had been so carefully cultivated evaporated under the quiet persistence of water and gravity. In hindsight, these early signs were a prelude, a series of soft alerts that were easily ignored, yet utterly critical. What seemed like perfection was a fragile balance, and the first night of heavy rain would test it in ways that no one had imagined. Beneath the grandeur of the dam's imposing walls, countless small decisions had quietly stacked themselves like hidden dominoes, each one seemingly harmless but collectively capable of catastrophe. In the planning rooms, engineers made concessions to deadlines, budgets, and political pressures. A change in concrete mix in one segment, a minor adjustment to a drainage channel, the relocation of a spillway by a few feet. None of these choices seemed consequential at the time. Each was justified, with a rational explanation, efficiency, cost reduction, or minor optimization. Yet together, they created vulnerabilities that no single calculation could predict. Subcontractors, under pressure to meet tight schedules, sometimes bypassed verification steps. Tiny gaps in the joint seals were overlooked. Small pockets of uneven compaction were left unaddressed, and the careful alignment of reinforcement rods was occasionally compromised. These minor deviations were noted in reports, but the language used downplayed their significance. Within tolerances, non-critical variance will not affect long-term stability. The project's culture had a subtle yet powerful insistence: trust the calculations, trust the design, and do not question authority. Even the engineers themselves, experts with decades of experience, fell prey to cognitive bias. Once they had signed off on the dam's integrity, they became less attentive to anomalies that did not fit the narrative of perfection. Early indicators of stress, small vibrations, micro cracks forming in concrete segments, sensors recording unusual pressure differentials, were rationalized as negligible, temporary, or anomalies caused by instrumentation error. Each overlooked warning, each silent nod of approval, made the structure less resilient than anyone dared admit. And then there were the compromises imposed by management. Budgets were tight, timelines unforgiving. Requests for additional reinforcement in certain sections were met with polite resistance. The plans already exceeded standard requirements, they were told. Delays would be politically damaging. The engineers understood that compliance often meant following a line between safety and perception. The public, and even the authorities overseeing construction, had been convinced that this was a dam beyond failure, a symbol of progress and mastery over nature. Human error was subtle, almost invisible. It manifested in delayed inspections, misinterpreted sensor readings, and unreported anomalies. Every decision seemed defensible on its own, yet collectively they created hidden weaknesses, latent stress points that no simulation could adequately reveal. Water would exploit these weak points with ruthless efficiency, flowing where calculations predicted it would not, pushing the structure toward a tipping point that no one could foresee in the comfort of daylight or the quiet of a design office. As night approached, the stage was set. The rain, that was expected to test the dam's resilience, did not merely apply pressure. It amplified every small oversight, every silent decision, every assumption that had been made. The perfect plan, trusted by experts, relied on a fragile equilibrium, and when one part of that balance began to fail, it would not be a gradual process. The small, quiet choices overlooked, rationalized, and accepted would collide with nature's unstoppable force, revealing the dam's vulnerability in the starkest terms possible. The night sky had been overcast for hours, but the meteorological reports predicted nothing extraordinary. Rainfall was measured, expected, and within historical norms, the type of weather the dam had been designed to withstand 100 times over. Engineers monitored water levels from control rooms and inspection posts, confident that the system's spillways and drainage channels could handle far worse conditions. Everything on paper suggested that this was merely another routine test of the dam's capacity. Yet, as the downpour intensified, subtle anomalies began to emerge. Water levels in localized areas started to rise slightly faster than anticipated. Pressure sensors embedded within the dam's structure registered minor fluctuations. These readings were small, each one easily dismissed as a sensor glitch or insignificant deviation from predicted values. Even seasoned engineers, trained to interpret minute changes in structural behavior, saw nothing alarming. The dam, after all, had been constructed to last for centuries. It was supposed to survive this. The rainwater, however, had its own agenda. It seeped into microcracks that had formed during construction and during the silent, overlooked compromises made months earlier. Through these tiny pathways, water infiltrated sections of the dam that had been assumed impermeable. It moved slowly at first, invisible to inspectors and undetectable by standard monitoring systems. But this infiltration gradually increased the internal pressure on critical zones. Engineers relied on simulations and historical data to predict how the structure would respond. They assumed the forces applied by the rain were uniform, that the concrete and reinforcement could absorb minor deviations, but nature does not conform to assumptions. The distribution of water pressure was uneven, interacting with the minor imperfections in the construction, concentrating stress in vulnerable spots. The dam, so confident on paper, was quietly being tested in ways no blueprint had ever accounted for. By midnight, the anomalies became more pronounced. Small leaks appeared along the dam's face, barely noticeable, barely audible, but ominous in their implication. The water whispered through unseen channels, exploiting the silent decisions that had left the structure subtly compromised. Even as sensors and alarms flickered with irregular readings, the engineer's perception remained that of control. It was a dangerous misjudgment, a confidence that had been carefully cultivated over years of design and construction. And yet, the rain showed no mercy. Every drop that fell increased the internal tension in ways that were invisible until it was too late. The sections previously considered non-critical began to respond unpredictably. Pressure readings rose in succession, creating a cascading effect. The dam was beginning to move toward its breaking point, a sequence that no engineer could stop once initiated. By the early morning hours, the combination of persistent rainfall and unseen structural weaknesses had shifted the dam from a position of passive endurance to imminent failure. What should have been a manageable storm had become a relentless force, slowly turning the engineers' assumptions against them. The rain, though ordinary in measurement, had become extraordinary in consequence. As the hours wore on, subtle signs of distress began to appear across the dam's massive form. It was not a sudden, catastrophic rupture, but a series of almost imperceptible movements that whispered a warning to anyone paying close attention. Tiny cracks, invisible in the dim light, shifted slightly, and small trickles of water appeared in places where no seepage had been recorded before. These were anomalies that could easily be dismissed, minor, perhaps inconsequential, but they were the first murmurs of a disaster quietly gathering momentum. Engineers monitoring the structure remotely noticed slight variations in sensor data, readings that oscillated in a pattern inconsistent with previous storms. A few of the most experienced supervisors felt unease, a nagging sensation that something was amiss. But the early morning reports reassured them. Everything was within design parameters. No alarm had been triggered, no emergency protocols initiated. The numbers suggested safety, but the numbers did not see the subtle interplay of forces building inside the dam's core. Inside the structure, water began exploiting hidden vulnerabilities. It found the smallest imperfections, areas where concrete was slightly weaker, where reinforcement bars were slightly misaligned, where tiny voids allowed seepage to concentrate. With each passing hour, the internal pressures shifted, and the dam's own weight and the rising reservoir water created tension in unexpected places. The very features that engineers had relied upon as safeguards now amplified the strain. The atmosphere on site was eerily calm. Crews noticed nothing unusual at first. The wind rustled the trees nearby. The rain pattered against inspection platforms, but there was no sense of impending calamity. Yet, in certain areas, subtle vibrations began to resonate through the dam's face. Faint tremors that could be felt if one pressed a hand against the concrete. These were the early tremors of a chain reaction that no calculation had predicted, the quiet precursor to complete structural failure. By 3 a.m., small leaks had grown into persistent streams in the lower sections. Microfractures extended minutely, but rapidly along the joints and supports. Water that had initially spread thinly now pooled in isolated areas, increasing hydraulic pressure in spots that had not been accounted for in simulations. The dam's outward appearance remained imposing and intact, but internally, it was beginning to fracture under forces that were invisible to the eye and misinterpreted by instruments. The subtle, strange behaviors continued to escalate. Sections of concrete emitted faint creaks, a sound almost drowned out by the rain, yet ominous in its implication. Sensors recorded pressure spikes in patterns that were irregular and difficult to interpret. What engineers could not perceive was that these early indicators were not random. They were the dam's response to cumulative errors, concealed weaknesses, and the relentless accumulation of water. Every minor anomaly was a step closer to irreversible collapse, yet to the outside observer, the structure still looked stable, almost untouchable, reinforcing the illusion of safety. And so, as the night pressed on, the dam quietly signaled its vulnerability. The first hints of its eventual catastrophic failure were already present, hidden in the whispers of concrete, the subtle shudders of water, and the anomalies the instruments failed to fully decode. Those who were monitoring it would never have imagined that what seemed like minor signs would, within hours, escalate into a disaster that would rewrite the understanding of structural failure in modern engineering. As the first light of dawn crept over the horizon, the dam had already begun a sequence of failures invisible to most eyes. Water had infiltrated critical zones, pressure had concentrated in areas originally deemed secondary, and the structure's internal equilibrium had been irrevocably compromised. It was at this precise moment, hours into the persistent rainfall, that the balance, the delicate trust between human engineering and natural forces, tipped beyond recovery. Inside the dam, microfractures had propagated along reinforcement grids. The very concrete that engineers had celebrated as impervious was succumbing to hydraulic pressure, stress lines intersecting and forming networks of instability. Sensors now registered unusual spikes, but the readings were fragmented, misinterpreted, and ultimately unable to convey the imminent reality. The dam, so confident in its own design, had quietly entered a phase of accelerated deterioration. A section near the base, where water had pooled unseen for hours, finally reached its structural limit. The concrete began to crumble internally, displacing the reinforcing steel and shifting the stress onto adjacent supports. This was not a sudden explosion, but a cascade, a sequence of incremental failures that multiplied the effect of each tiny compromise. A section that had been expected to withstand centuries of stress now buckled under a few hours of rain, a testament to the cumulative consequences of minor oversights and silent concessions made during construction. Engineers monitoring the dam from the control room still assumed safety. Alarms had not yet sounded. Pressure relief valves were in place, but they were being overwhelmed by the concentrated force of water, finding every available weakness. The internal drainage system, designed to distribute and reduce pressure, had been partially obstructed by construction variances and sediment accumulation, further exacerbating the problem. Nature, patient and relentless, exploited each imperfection with precision. At the exact point of failure, water began to breach the dam's lower sections, forming small surges that quickly coalesced. These surges increased lateral pressure on adjacent walls, forcing joints to separate. The sound was subtle at first, a low groan that resonated through the concrete, yet it marked the beginning of a chain reaction that would culminate in disaster. For those nearby, the dam remained imposing and seemingly solid, but internally, the structure was unraveling. The physics of failure had been set in motion. Once the first critical section gave way, stress redistributed unevenly, and previously stable areas became overloaded. Cracks propagated at a geometric rate. Water followed the path of least resistance, and the internal harmony that had held the dam together collapsed in. Minutes what engineers had predicted to endure centuries had begun to fail in hours. By the early morning, before anyone could react, the dam had transitioned from a state of imperceptible stress to uncontrollable collapse. Every section that had appeared sturdy on inspection reports was now compromised. Every calculation of safety margins rendered moot. The disaster was no longer theoretical. It was unfolding in real time, propelled by the perfect storm of rainfall, unseen weaknesses, and the cumulative effect of decisions made long before. The moment the dam gave way, it did so with a terrifying swiftness that no engineer, inspector, or onlooker could have anticipated. What had been a massive, seemingly unyielding structure, praised for its strength and longevity, transformed within minutes into a torrent of destruction. The water, once contained and obedient, now surged forward with an unstoppable force, carrying debris, concrete slabs, and the accumulated power of a reservoir that had grown silently overnight. It began at the base, a critical joint, weakened by hours of hidden water infiltration and unseen stress, fractured first. The concrete groaned and shifted, tiny fragments scattering into the air like shrapnel. Then, as if awakening an unstoppable chain, the adjacent segments cracked, one after another. Reinforcements that had been designed to distribute the load were overwhelmed, snapping under the sudden force. Water found every path, and exploited it mercilessly. The first wall buckled, sending a surge over the crest, a violent wave that tore at every downstream structure in its path. Machinery, observation platforms, and inspection sheds were lifted and swept away. The roar was deafening, a combination of cracking concrete, tumbling debris, and the relentless rush of water. Trees lining the riverbank were uprooted, vehicles and equipment flung like toys. The dam's collapse was not a single event. It was a series of rapid, sequential failures that fed on themselves, each fracture intensifying the next. The night's persistent rain, once considered manageable, had saturated the surrounding soil. This saturation softened the earth, supporting the dam's abutments, allowing the massive hydraulic forces to shift foundation material. Entire sections of the dam's face slid downward, chunks of concrete breaking free and plummeting into the swirling torrent. The water followed, widening the breach with alarming speed. Communities downstream had mere minutes to react. The warning systems, if any, were overwhelmed or delayed. By the time the first sirens sounded, the surge was already approaching populated areas, carrying destruction far beyond the dam itself. Boats, bridges, and infrastructure were torn apart in the path of the water. Roads turned into rivers, and buildings crumbled under the pressure. The collapse was total, instantaneous, and merciless. In those fleeting minutes, the dam that had been promised to endure for half a millennium became a cautionary tale. Engineers, confidence, simulations, and assumptions were rendered irrelevant by the raw, unyielding force of water. The structure's failure was a violent revelation that even the most meticulously planned projects could be undone by small oversights and the unpredictable power of nature. And yet, amidst the chaos, some sections of the dam held longer than expected, providing glimpses of resistance before succumbing. These moments of temporary stability were fleeting, but gave a horrifying rhythm to the collapse. One crack, another, then total failure, a sequence no one could have survived unscathed. As the last remnants of concrete and reinforced steel were swept away, the disaster was complete. The dam's destruction carved a permanent scar into the landscape, leaving behind a river channel transformed, infrastructure obliterated, and communities devastated. The engineers' predictions of longevity and invincibility were gone, replaced by the stark reality that human calculation could never fully contain nature's unpredictability. As the dam's remnants disappeared into the churning waters, the catastrophic force surged downstream, transforming landscapes and lives in an instant. Entire river valleys were swallowed by the torrent, buildings and bridges pulverized or washed away. What had once been a community, thriving and orderly, was now a scene of chaos. Roads turned to rivers, homes ripped from foundations, and vehicles flung as though they were toys in the hands of an unseen giant. The raw power of the water left nothing untouched, a devastating reminder of how quickly human constructs can be rendered powerless. The initial shockwave of destruction reached towns located several miles from the dam in mere minutes. Residents awoke to a monstrous roar, a sound unlike any storm they had ever experienced. People scrambled to higher ground as the water engulfed streets and buildings. Emergency response teams, if they existed, were overwhelmed, hampered by blocked roads and rising currents. The sheer speed of the disaster rendered traditional evacuation plans nearly useless. Industrial facilities along the river bore the brunt of the deluge. Warehouses, power stations, and chemical plants, designed for centuries of operation, were inundated within moments. Machinery was destroyed, storage tanks ruptured, and hazardous materials released into the environment, compounding the human and economic toll. Rivers became conduits of devastation, carrying not only water but debris, oil, chemicals, and rubble downstream. Ecosystems were shattered, fish and wildlife decimated, soil eroded, and the landscape altered permanently. Casualties mounted quickly. People trapped in low-lying homes or along riverbanks were swept away, while others survived only by clinging to trees or debris. The death toll grew as the floodwaters carved paths of destruction, making it impossible for rescue teams to reach everyone in time. Communities once safe behind the dam were suddenly exposed to nature's unchecked force, a stark reminder that infrastructure failures can escalate faster than any emergency plan anticipates. Communication systems failed under the torrent. Telephones, radios, and early warning mechanisms were inundated or destroyed, cutting off coordination between emergency personnel. Those who survived the initial impact faced isolation, confusion, and the terrifying uncertainty of what lay ahead. In the hours following the collapse, the floodwaters continued their relentless march, leaving a landscape that was unrecognizable, stripped of familiar landmarks, and buried under silt, debris, and the remnants of human ambition. The economic toll was staggering. Transportation networks destroyed, businesses ruined, and essential services paralyzed. Agricultural fields were submerged, livestock lost, and food supply chains disrupted. The full consequences of the disaster would unfold over months, even years, as communities struggled to rebuild, reconcile losses, and understand how a structure deemed unbreakable could fail so catastrophically. This immediate aftermath revealed the profound human cost of engineering failures. It wasn't just about concrete and steel. It was about lives, homes, livelihoods, and trust in systems that had been assumed reliable. The dam's destruction became a living lesson. No matter how perfect a design appears on paper, neglecting small anomalies and underestimating natural forces can produce consequences beyond imagination. In the aftermath of the collapse, investigators arrived on site to assess the magnitude of the disaster and to determine why a structure guaranteed for 500 years had failed in a single night. The first impressions were overwhelming: shattered concrete, twisted steel, uprooted trees, and debris strewn for miles. It was clear that what had seemed impossible was now an undeniable reality. Yet, amidst the chaos, experts began to uncover patterns, subtle signs that the dam's failure was not solely the result of the storm, but of a series of human and technical errors that had quietly accumulated over years. Initial inspections revealed inconsistencies in construction that had been overlooked or downplayed during the project. Reinforcement bars were misaligned in critical sections, concrete thickness varied beyond the accepted tolerances, and drainage channels had been partially obstructed by construction debris. These were not catastrophic on their own, but in combination, they created points of weakness where water could infiltrate and pressure could concentrate. The investigators noted that many of these flaws had been recorded in internal reports, yet were dismissed as non-critical deviations. Further analysis focused on the design assumptions made during the engineering phase. Models assumed ideal conditions: perfect concrete compaction, uniform material strength, and predictable water flow. In reality, natural variations in materials, minor human errors, and environmental conditions combined to produce stresses that were never anticipated. Sensors installed to monitor the dam had detected unusual vibrations and microleaks, but these warnings were misinterpreted or ignored because the readings remained within the predefined safe thresholds. The investigation also highlighted decision-making failures. Management pressures had led to compromises in both construction and oversight. Requests for additional reinforcement in vulnerable sections had been rejected to maintain budget and schedule. Supervisors assumed that adherence to the original plan was sufficient, even when early warning signs appeared. The very culture of unquestioned trust in calculations and certifications contributed to a lack of vigilance, creating an environment where minor errors went unchallenged until they became catastrophic. Engineering experts concluded that the collapse was a systemic failure. No single mistake had caused it, but rather a combination of small errors, overlooked warnings, and unrealistic assumptions that had accumulated over time. The dam's failure was as much a product of human oversight and organizational complacency as it was of natural forces. The rain merely accelerated a process that had already been set in motion by silent, preventable misjudgments. The findings shocked the public and the engineering community alike. A structure deemed invincible had been undone, not by an extraordinary storm, but by a series of ordinary, unnoticed mistakes amplified under stress. The report emphasized that even advanced models, high-quality materials, and rigorous standards cannot compensate for poor communication, ignored anomalies, and small compromises during construction. Lessons from this investigation would reverberate for decades, reshaping safety standards and forcing engineers to confront uncomfortable truths about human fallibility in projects of monumental scale. The dam's collapse left more than just a scar across the landscape. It left a permanent lesson etched into the collective memory of the engineering world. In the aftermath, as communities rebuilt and river valleys slowly recovered, professionals and regulators alike were forced to confront an uncomfortable truth. Even the most meticulously designed structures are vulnerable when human error, oversight, and misplaced confidence combine with nature's unpredictability. The disaster became a case study in failure, a sobering reminder that no amount of planning can entirely eliminate risk. In the months following the catastrophe, engineering standards were revised, safety margins were reassessed, inspection protocols strengthened, and risk assessments made more conservative. What had been considered best practice before the collapse was no longer sufficient. Engineers learned that microfractures, minor mistakes, and overlooked anomalies could become the fulcrum of a catastrophic sequence, and that, ignoring these details, even when simulations suggest safety, can have fatal consequences. Beyond technical lessons, the event highlighted the critical importance of organizational culture. The silent decisions, the ignored warnings, and the pressure to adhere to schedules over safety all contributed to the disaster. companies began to emphasize the need for rigorous communication channels, transparent reporting, and empowering field engineers to escalate concerns without fear of reprisal. Training programs incorporated case studies from the collapse, using real-world data to demonstrate how cumulative small errors could become a chain reaction, capable of toppling what appeared to be an invincible structure. The dam also left a lasting imprint on public perception. Communities affected by the collapse demanded accountability and transparency. The disaster shattered the myth of invulnerability often associated with large-scale engineering projects. Media coverage and academic analysis dissected the event from every angle, exploring not only the technical failures but also the human factors, complacency, assumptions, and blind trust in calculations. These narratives served as a chilling reminder that the consequences of engineering mistakes extend far beyond blueprints, affecting lives, livelihoods, and entire ecosystems. Decades later, the lessons of this failure remain deeply relevant. Modern dams, bridges, and infrastructure projects now incorporate layers of redundancy, continuous monitoring, and independent review processes designed to catch subtle anomalies before they escalate. Engineers worldwide study the collapse as a benchmark of how high stakes and small oversights can intersect, and how critical it is to question assumptions, test limits, and remain vigilant under all circumstances. Ultimately, the dam that was meant to last 500 years became a symbol of hubris and human fallibility. Its collapse demonstrated that nature will exploit every weakness, every minor decision, every oversight, and that engineering excellence is only as strong as the attention and vigilance applied throughout the project's life. The story of this disaster is not just a tale of failure, but a vital lesson. Continuous vigilance, respect for nature's unpredictability, and humility before the forces we attempt to control are essential for survival in the world of industrial engineering. If you made it to the end of this video, take a moment to reflect on what you've just witnessed. The story of this dam's collapse is more than a technical failure. It's a stark reminder of how small oversights, ignored warnings, and misplaced confidence can lead to catastrophic consequences. We want to hear your thoughts. Comment below with your theory on what could have been done differently to prevent this disaster, or share your reaction to the magnitude of the collapse. Your perspective is valuable and sparks important conversations about engineering, safety, and accountability. If you found this story compelling and want to continue exploring real-life industrial disasters, make sure to hit the like button and subscribe to the channel. By subscribing, you'll stay updated with more in-depth analysis, lessons from history, and dramatic stories that reveal the hidden risks behind human engineering. And don't stop here. Check out the next video, appearing on your screen now. It dives into another unbelievable industrial catastrophe, exploring the mistakes, oversights, and events that led to yet another shocking failure. Stay curious, stay informed, and keep learning from history so that the next disaster can be prevented.